Hi, I present our paper OdoViz, a 3D odometry visualization and processing tool by Saravana Balaji Ramachandran, myself, and Professor John MacDonald. OdoViz is a web-based 3D visualization and processing tool for autonomous driving and mobile robotics datasets to support common tasks in visual place recognition research. Recently, a lot of image-based autonomous driving researchers increasingly use machine learning-based techniques. ML-based techniques need a lot of data. In picking the right dataset from a bunch of publicly available driving datasets, processing and utilizing them to curate the right data for training, there are some challenges involved. Many of these datasets provide only a top view of the trajectories included. So it is hard to visualize the overlap between the trajectories, to determine the pose density, and to inspect the individual pose information. Also, there are different conventions used by different datasets. For example, the file formats. It could be NVM, log files, CSV files, or space-separated text files. Coordinate systems used when recording these datasets can vary as well. Ideally, software development toolkits, or SDKs, are released alongside these datasets to simplify their use. However, one has to code for additional tasks for curating the training set, such as sampling images, collecting data associated with the images, and for finding pose correspondences. Given the variations in the API and the use of different programming languages, the code written for these additional tasks will have limited portability across these datasets. So here are some of the tools for visualizing driving data. So Visual SFM is a full-fledged structure from motion tool, and it loads and exports NVM and image files. WebViz is a ROS-backed processing tool. It can process from live robots simulation or from saved files. Autonomous Visualization System, or AVS, can load trajectories and navigate through individual poses, point clouds, and images on a frame-per-frame basis. Open3D and its recent ML extension edition supports visualizing data and results for common 3D tasks such as object detection, semantic segmentation, etc. Many of these tools provide rich frameworks for processing and visualization at the local level. So we can visualize an individual pose and inspect the data around it, such as the point clouds. But viewing trajectories as a whole is more of a global level task. Many of the tools here are not directly applicable for these global level tasks, especially for finding pose correspondences within and across trajectories, visualizing loop closures, etc. So we developed OdoViz to load, visualize, and process complete trajectories. It can handle GPS INS poses, point clouds, camera images from datasets. In addition to supporting popular driving datasets, it can also support custom or new upcoming datasets by simply adding new parser files. And the functionality of the software can further be extended using custom extensions and plugins for other potential data management, visualization, and processing tasks. We have open sourced the tool under MIT license on GitHub. We have also hosted a live instance of OdoViz at odoviz.cs.neom.ie for demo purposes. OdoViz has out-of-the-box support for popular driving datasets. This includes Oxford Robot Car, CMU Seasons, PDD 100K, St. Lucia, New College, and Kitty Odometry. We further include plugins and extensions for analyzing top K matches in an image retrieval benchmark and for visualizing topological nodes of a trajectory. OdoViz is web-based, powered by a thin server serving the data and a rich client handling all the data from the server. And it separates the handling data part by storing all the data that's necessary to run the software in a store. And any changes made to the store will trigger updates in the UI and the 3D environment. This kind of structure makes OdoViz to be extensible, and it allows processing the poses in an asynchronous manner while updating the 3D environment without affecting the main UI thread. Being web-based, it also allows multiple deployment configurations. It can be used as a single-user software in a separate computer, or it can be used in an organization with a central server, with the users of the organization separately consuming the data from the server and visualizing them on their own machines. It can also be used as an online interactive visualization tool for datasets, allowing users to explore, navigate, and inspect stuff within the trajectories included in the dataset before downloading them. We can also limit the amount of data that's being served and the number of processing features, and we can even allow people to selectively download the trajectories that they want. So OdoViz is made up of 4 core modules. One of the main ones is data parser. So each dataset is associated with a data parser. Data parser for any dataset will consistently return a list of poses with all the data necessary, and this list of poses will be loaded into the browser memory and will then be used for further tasks like visualization, sampling, finding pose correspondences, etc. So this makes it easier for writing new parsers for supporting new datasets without touching the rest of the software. During data parsing, any compute-intensive tasks can be performed either on the client side or on the server side. So next we have the offset settings. In order to catch up with the different coordinate systems that can be used when capturing the dataset, we provide various settings. So we can adjust the offsets in all the 6 axes, 3 rotational and 3 positional. We can invert the values in each of them, swap them, and even scale them. There is an additional feature where we can ignore the GPS altitude, which is represented in z-axis, and replace it with timestamps. And this is very useful for visualizing the overlaps, for visualizing loop closures, etc. Then we have the scene settings. So it provides useful settings to switch between top view, perspective view, switching off lights and grids, changing the controls, and adjusting the size of the 3D model shown in the 3D environment. OdoViz also has support for point clouds. It'll show point clouds with depth colored in Viridis color map. So finally, we have the info and image viewer. Hovering on any of the poses will select the pose, and associated information can be viewed in the info viewer and the image in the image viewer. If GPS coordinates are associated with the pose, then a minimap shows the location of the pose. It's an interactive minimap powered by Leaflet, and we also have integrations with Google Maps and Google Street View by using GPS and heading. Because of the hover-based selection, we've also added a feature to pin the selected object to lock selection temporarily. OdoViz supports common tasks used in visual place recognition research. This includes adaptive sampling and finding pose correspondences. In many datasets, we have quite a lot of data points, and rendering them all in a 3D environment would be very computationally expensive, and each processing step performed after that will add additional latency because of the number of poses. A common solution is to uniformly sample the poses. However, as you can see in the contours, there is a lot of loss of information around the corners because of uniform sampling. We introduce adaptive sampling, which takes into account both the distance between the poses and the angle or the heading for each of the poses. By only having 5 to 10% extra poses, it preserves the corners. So next we have the pose correspondences. Once the main trajectory is loaded, we can load more trajectories to find pose correspondences. For each pose in the main trajectory, we pick the pose with the least loss in the trajectory to be matched. And 2 poses cannot be matched with 1 pose in the main trajectory. And this is more like the marriage problem. We calculate the loss by including both distance and heading. to ensure the matched poses have maximum visual overlap. So an example where we overlap 3 trajectories and find pose correspondences is shown here. Both for sampling and for pose correspondences, the results can be downloaded in JSON format for further training of machine learning models. For more details on the loss function and algorithms used in these techniques, please refer to our paper. So, as I mentioned earlier, OdoViz's functionality can be extended by adding extensions and plugins. So here, we provide visualization and compute plugins for 3 different tasks. So first, we have the Save and Restore plugin. It's a simple import-export plugin for saving and loading the current viewpoint, scene and offset settings, sampling settings, and the loaded file. We also have provided indicators, which are useful to know if the data has changed since the last load. One of the important evaluation methods for learned visual representation is image retrieval. So these learned representations or embeddings improve over time over the course of training. We can log the embedding distances at certain intervals every 50 epochs, for example, using PyTorch or TensorFlow, and later we can load the logged distances using this extension to visually analyze the top K matches. So there's a slider for changing the top K matches and to adjust the steps or epochs. In this example, we can see that the embedding for a nighttime image has matched with a daytime image and it has ranked in the top 5 retrieval. So it is useful in these cases to analyze visually the top K matches. And finally, we have the Hasty Map extension. Hasty Map is an approach introduced by Garcia et al. 2017. It divides the trajectories into locations or topological nodes containing similar set of images, and by hierarchically dividing the trajectory into locations, we can speed up the loop closure candidate searches. So this extension loads the results of Hasty Map and it colors each location or topological node in a different color. So it also shows connection between images indicating loop closures. So in this paper, we have presented OdoViz, a new web tool for simplifying tasks of utilizing autonomous vehicle datasets within ML research. Thank you.